I am going to present a little bit about how to set up a simulation and solve a DEM problem using Rocky DEM. So I would like to start this presentation saying that Rocky has some unique features, as we can see in this slide. The first of these key differentiators is that we can simulate any particle shapes that we want, taking into account the actual particle shape of the material to be analyzed. We can also use realistic breakage models in Rocky, which allows us to preserve mass and volume of particles with accurate particle shape representation. Rocky also has multi-GPU capabilities, which means that we can simulate large particles count and complex particle shapes problems. Rocky is also fully integrated with ANSYS products, meaning that we can combine particles dynamics with fluid dynamics or perform structural analysis due to particle loads. It is also possible to have geometries moving in all 6 degrees of freedom as they interact with particles, without the need of coupling with any other software. Finally, we can customize our simulations by creating different models of or modifying existing ones. So in Rocky, there are 3 different categories for particle shapes. Fibers, which have one principal dimension and can be used to represent hay, for example, in a hay baler equipment. We can also have shells that have 2 principal dimensions. And here we can see one example of a potato chip in a seasoning drum. And solids, which can be convex or concave. And these solids can have any other particle shape that we want. Here we are showing a polishing machine with nuts and bolts in it. And as we see here, these shapes are quite complex, but we can easily accommodate that in Rocky simulations. With that being said, I would like to show you a few examples. The first one here is a tablet counter. It is a tablet counter machine. And as we can see, we are using the actual tablet shape. We are doing a coupled simulation with the ANSYS Fluent. And here, with this type of coupling, we can do momentum transfer, heat transfer, and mass transfer between these different phases. So here we are adding liquid to these particles. And as we see, as time moves on, we are adding liquid to some particles according to the region where they pass by. So this liquid is transferred between particles as well. And this also takes place into the forces that are acting between particles. So we have adhesion forces between particles. And as this hot air passes through this particle bed, we see that particles' temperatures also increase. So with these types of problem, we can analyze the liquid drying as well that was added to the particles. After a certain time, we see that the temperature increases, the particles' temperatures increases, and since the temperatures increases, we can see that the liquid mass inside each tablet is being reduced over time. And this liquid, in this model, the liquid will be removed according to the particle's temperature until we have no liquid in the particles anymore. And we will only remain with some mass in the particles, that is the solute mass. So when there's no more solvent, the particle's temperature will increase again. So this type of simulation can be used to do optimization analysis, to evaluate different processes, parameters like the drying air temperature, the airflow rate, and everything else like the batch load can be changed as well. So in the second example that I want to bring here is another tablet coater, but in this case, we are not evaluating the deposition of liquid on particles according to a specific volumetric region. We are adding liquid according to the particles that are visible to the spray zone. So only the particles that are visible on the top layer here will receive liquid content. And that is actually more representative of the real process that actually happens in the experiments, right? So once with Rocky, we have module that allows us to analyze the deposition of this liquid content on the surface of the tablets, and we can evaluate the coefficient of variability over time as this liquid is being added to the particles. In such applications, we want this variability to be below certain values. In this case, we want to achieve a value of 6.25, and we can extrapolate this data to estimate how much time we would take to reach this 6.25%. So we can perform other types of analysis as well, like transforming our discrete results into a continuum results using the Eulerian statistics. So here on the left, we can see how we are evaluating the stress component in the tangential direction for these tablets. But we can also analyze information at particle level. So for this example, for tablet coater, we can evaluate different particle shapes, like we are seeing here on the right. And in this case, we want to reduce the stress components on these tablets, because these stress components will cause these tablets to break, or we will see some edge chipping here, as we are seeing in some shapes. And we can see here that for this shape here on the right top corner, these stress components are reduced. So this would be the best particle shape for this specific application. Now, not only we can evaluate different particle shapes that are very complex, but we can also evaluate problems with extremely high particle counts. And in this next example, I'm showing you mixing a ribbon mixer, where we are simulating approximately 30 million particles, which is a very high number of particles. So for this specific case, we started our simulations using 2 Tesla V100 GPU cards, and the pace for each second of simulation was 1.45 days. As we can see here in this plot, when using other cards, better cards, we can reduce the simulation pace and run these simulations much faster. So when using 2 A100s, we were able to reduce the pace in about 25%. And when increasing the number of GPU cards, we can reduce this simulation pace, which is the time it takes to simulate 1 second of simulation, in to less than a half day to run each second of simulation. And in such applications, the main goal is to evaluate the mixing efficiency of such equipment. So we start our simulation here with the main product, and then we added some other materials here. The first one was an additive, and then we added a cohesive additive. And then as time goes by, we can see that these products are being mixed. And in Rocky, we can create expressions to evaluate the mixing efficiency, like the Lacey mixing index. This Lacey mixing index is basically mixing index that allows us to evaluate how well mixed these particles are. And the closer to 1 this index is, the better mixed our product is. And once we reach a value of 1, it means that we have a homogeneous mixture. And as we can see here in this video, we can evaluate different regions where we have this mixing. We can create sections to see how this granular material is distributed inside this mixer. And we can also try different ribbon designs to see which one would be the best for our application. Okay, so without any further ado, I would like to do a quick demo here to show you how can we create a simulation in Rocky. So this is Rocky's interface. We start selecting our physics models. Then we can enable a few modules here to collect some information between particles or to get the frequency of collisions, for example. After that, we can then import our geometries and save our simulation. Once that is being done, we just need to select the unit that we used to create this geometry. And here we can see our geometry that was imported. We can change a few visualization options, like changing the transparency, change the color of it. We can also change the background color for a better view. And then we just need to create our motion for this geometry, for this quarter. Here we are going to add a rotation motion, and we are going to use 12 rotations per minute. The next step is to define the materials properties. And once we define the motion, we need to link it to the geometry. And here we can see a preview of the motion before we even start the simulation. So we don't need to spend time running our simulation to realize we made a mistake on our motion frame. We can do that before we actually start the simulation. Then we define the material properties. We define the interactions between these different materials that we have in our simulation. Here I'm changing the friction between particles and the friction between the particles and boundary. We can also change the restitution coefficient. And then we create our particle. For this specific case, we are going to use a custom polyhedron. So we are going to import a tablet shape that we draw and we saved using an STL file. And here we have our particle shape. We can then change its size. And in this case, we are going to use a volumetric fill. So with the volumetric fill, we are going to inject a certain amount of particles at the beginning of our simulation. So all particles will be injected at once, and we don't need to spend time injecting these particles over time. Now, let's go back to our 3D view. I'm going to enable the contacts here, change the simulation time for this case, select the hardware that I will use for this case, and I'll start the simulation. Okay, so then we just need to wait until the simulation is over. And here I already have these results post-processed and finished. So once the simulation is done, I'll show you how can we do a few things here. So the first thing I'll do is I will import polyhedron, which defines our spray region. And with this polyhedron, I want to evaluate the time particles spent inside this region. So based on the time these particles stay inside this region, I will correlate that with the amount of liquid that they would receive from this spray. And I can do that by using the residence time for this polyhedron. Rocky will compute this residence time, and we can do a correlation of the liquid that is being deposited on particles with the time that particles stay there. So we can evaluate, we can do an analysis of the coefficient of variability for these particles based on the time that they spend there. I'm showing you here how can we change the visualization options for these particles. So here, the more red the particles are, the more time they spent inside this region. We can also see particles by particles velocity, for example, and I can create a plot that allows me to see the average velocity of all particles in this simulation. So all this post-processing analysis can be done inside Rocky itself. We don't need to export this data to do this analysis in any other software. And here I'm showing you here how can we create a particle trajectory. So For a particle's trajectory, we just need to select a certain instant in time. And based on the time that we selected, these trajectories will be created. And here we have all trajectories colored by black lines, but we can color these trajectories by a certain property like the translational velocity of tablets as well. We can also create some statistical properties here inside Rocky. So for example, if I want to evaluate the frequency of collisions between particles, we can create a custom property to analyze that inside each tablet that we have. For example, here we are looking at the frequency of collisions in each position of the tablet. So this single tablet is representative of every other tablet that we have in our domain. And this means that where we have these red regions is where we have more collisions happening among all the tablets that we have in our simulation. Okay, so that was basically what I wanted to present to you today. It's just to give you an idea of how easy it is to create a simulation and do the post-processing using DEM.